Hello everyone, and welcome to another edition of the Latin American webinars on physics. My name is Federico Montarpalen, and I will be your host today. Today we have a really interesting talk because Eric Vázquez Jáuregui will tell us about the latest results from PICO. So we're really happy to have Eric Vázquez Jáuregui as our speaker today. Eric is at the UNAM in Mexico, and he has received his PhD from the Autonomous University of San Luis Potosí in Mexico, and has been a research scientist at SNOLAB. So before we start, let me remind you that you can ask questions via our Twitter feed, LAWOP, and the questions will be asked after the talk. So Eric is now a research associate at the UNAM, and he will tell us about dark matter research results from the PICO-60 C3F8 bubble chamber. So now let me pass you to Eric. Hello, Eric. Now you have to unmute yourself.
Okay, I think now it's fine, right? Can you hear me?
Yes.
Okay. Thank you very much for the invitation to this webinar. And I'm going to talk about the results that we recently published of the PICO-60 C3F8 bubble chamber. This is our largest chamber operating at SNOLAB. And I will present you the data the results from the data that we took on December and January of December 2016 and January this year. We use the technology that we use to search for dark matter is with superheated liquids in bubble chambers. Let me first give you an overview about the dark matter problem that you have certainly here. We basically know that about 85% of the matter in the universe is not baryonic matter. This is coming from an impressive number of observations on different scales. This is the pie chart of the contents, the matter energy content of the universe, with roughly 5% is what we see in the standard model of particle physics. And this is, as I mentioned, from an impressive number of observations. And this is just a summary that has on one side to the left, you can see the rotation curves of galaxies started by Zwicky and then continue with the discoveries made by Vera Rubin. It has also been measured with X-rays in galaxy clusters, where you can determine also the mass present in those clusters, and from gravitational lensing that tell us the matter present in between the lensed object and us. And on the right, you see what it comes to precision cosmology and also the cosmic microwave background. In precision cosmology, we have basically measurements from supernovae and acoustic baryon acoustic oscillations. We have the predictions from Big Bang nucleosynthesis. All these fits well in the lambda CDM framework, as we know, with some problems still. And then also these simulations of structure formation, where basically in the viable models, they are dominated by cold dark matter. So what do we know about that dark matter? Well, we know that it interacts gravitationally, that it has to be stable or long-lived at the edge of the universe. It doesn't have to be, it is not possible that it is relativistic. It has to be cold or warm. It is non-baryonic. It has to be electrically neutral. And it basically, if it interacts, it should be very fiddly, besides the gravitational force. So this, when we check the standard model of particle physics, we can basically cross over all the particles there. And this means that we are in front of physics beyond the standard model. And we have many possibilities. We have many masses, range of masses, for the possibility of this particle with many different cross sections. And basically, it spans many orders of magnitudes. And here you can see basically 20 orders of magnitude with different candidates. What are the basically the two candidates that attract most of the activity in the field? Well, we have the WIMPs, the weakly interacting massive particles, similar to a candidate which would be a neutral heavy fermion, like the lightest supersymmetric particle in SUSY. There are other theoretical candidates and from other models with many production mechanisms. And also there is this other candidate attracting recently the attention of scientists, the axions, that, as you know, were introduced in this problem for the strong CP. And well, there have been other candidates besides the axions, like the ALPs and dark photons. And the work that I am reporting here, it's on the WIMPs. This is the most discussed candidate so far. It's a particle that interacts weakly, and basically it was produced during the Big Bang. And when this particle in the beginning was in thermal equilibrium, as the universe cooled down, it decouples. Basically, with the cooling, it also comes the expansion, and very rarely particles, these WIMP particles, find each other to annihilate, and that basically gives a freeze out on these WIMPs. And they still should be around today. The densities that, of course, depend on the mass of the particle. There should be a few per liter. And well, basically, we don't know anything about this dark sector. I just mentioned a few, one example on the SUSY models, but the true thing is that we don't know how this dark sector could couple with the standard model. I mean, there's actually no reason to believe that there is only one particle. It could be more than one. It could be as in the standard model, as rich as the standard model. What are the detection methods for these WIMPs? Well, I just mentioned about all the astrophysics and cosmology measurements. We can also search for these particles through what we call direct detection, which is basically WIMP scattering. And there's also the possibility to search for annihilation or decay in the center of our galaxy, for example, that is called indirect detection. And it could be produced in accelerators, and basically trying to search there for missing energy that will point to a new particle that could be a dark matter candidate. My work and the work in the PICO collaboration is in direct detection. Basically, what we expect is one of these WIMPs. We are in this halo of dark matter that scatters elastically with nuclei, and we detect the recoil of this nucleus. And well, we need to calculate the rate based on some assumptions about the distribution of the dark matter and the interaction there has been two interactions. They are not the only ones, of course, but they have attracted the attention of the experimental scientists. One that couples to a nucleus and to all nucleus basically, and it is enhanced for large nuclei that we call spin independent, and we have the spin dependent that couples to the spin of the nucleus. And you can see there just how we could determine the cross section. But let me show you a more detailed or a more detailed example of what we do calculating these cross sections. Well, this is basically a cartoon where you have a WIMP coming and scattering on the nucleus. The problem is that we also have neutrons producing the same interaction, the same process that can scatter the nucleus of the atom. And we also have photons and electrons that can produce electron recoils. And basically, they deposit similar amounts of energy, and that could mimic the signal that we are looking for. This is basically how we can calculate an example of a rate calculation. The differential cross section that you see here. This example is just for spin independent. And you see the 4 parts that are included, basically the dark matter density component. This comes from observations and in the galaxy, well, in local and galactic observations. And this basically includes, as you can see, the mass of the particle that we don't know. We also have in red the particle physics component, basically the cross section. You see 8 there included, the atomic number, because it goes with, since it is an example for a spin independent, it scales with the mass, this cross section. And then you have a nuclear part in yellow, basically how we represent the nucleus. And then you have also the velocity distribution of dark matter in the galaxy. And well, we can measure experimentally the rate, the number of events per kilogram per kV. And we don't know the mass of this dark matter particle. We don't know the cross section. And basically, we can make this space parameter plot. You have there, you probably have seen it before in other talks about that basically shows you the cross section and the WIMP mass. This is only a cartoon where you can see in red areas that had been ruled out a couple of years ago. Some of the candidates, the asymmetric dark matter, the generic WIMPs that I just mentioned in the SUSY or Kaluza-Klein models. And in yellow, you can see the neutrino floor, basically the interaction of neutrinos with the nuclei, producing this scattering, this coherent scattering, and depositing energy in the nucleus. So how do we catch one of these WIMPs? Well, starting from the point that we live in a dark matter halo, we have some local density of around 0.4 GeV per cubic centimeter with some velocity. And to look for this scattering, we have there in a cartoon a piece of material in red and a WIMP basically scattering off the nuclei and producing this energy deposition. The problem is that we have many backgrounds, as I mentioned in this cartoon, that can produce similar signals that can mimic what we are looking for. They are less abundant than what we are looking for, dark matter, but they interact more. And we are looking for energy depositions of a few keV, and the rates are of the order much less than 1 event per kilogram year. And all these backgrounds for natural radioactivity could be beta decays. These beta decays, we can remove them by screening and purifying the detector materials. by careful choice of the materials that we use to build our detector. We also look for patterns to discriminate between these electron tracks and the nuclear recoils that would produce dark matter. We also have another background that could be alpha decays. This is solved with the same, similar to beta decays, screening and purifying. And also we look for some discrimination between the energy deposition of the WIMPs in the, that is of the order of keV to these alpha decays of the order of 5 MeV and above. And then we have the neutrons. These are the most dangerous one. They are produced by fission, alpha end reactions, cosmic rays, and they produce similar scatters on the nuclei as the WIMP. And for this, what we do is we shield our detector. We also do a careful selection of the materials. And we also need to remove these neutrons and muons. We need to go underground. Another possibility is also to reject multiple scatters. Since the mean free path of neutrons, it's a few centimeters in the materials that we use, while we can reject these multiple scatters since WIMPs will not do that. So once we are on the ground, we carefully selected our materials, and we also shielded our detectors. You can see there 2 examples of shielding. In white, one to stop neutrons, could be watered as a non-expensive option. And then we also, in some detectors, people use lead, for example, to stop gamma rays, which is also an important background for some experiments. And as I mentioned, at some point, the experiments will reach the sensitivity for this coherent neutrino scattering, which basically we have no way to discriminate, and we will need to find a new mechanisms to detect, to discriminate basically this neutrino scattering. Basically, this is the recipe for direct detection. We basically need to detect these tiny energy depositions of the order of tens of keV, a few keV. This is just a simple calculation that you can see that for our 100 GeV WIMP mass, we would have up to 50 keV of energy deposited in a nucleus. And the 2 plots that you see there, it's the importance of the energy threshold in our detectors. You can see there the rate for both plots. It's the rate in counts per 10 kilogram per year for a cross section of 10 to the minus 45 square centimeters. And this is for 2 WIMP masses, 100 GeV and 10 GeV. And what you can see, the importance of the threshold is that if, for example, you take one of these isotopes, the argon, for example, you can see that for a threshold of 20 keV for 100 GeV WIMP mass, you can see that the rate is close to 0.3 counts per 10 kilogram per year. And if the WIMP particle is only 10 GeV, you can see that at the same threshold, the rate decreases a few orders of magnitude. So no, the energy scale and the efficiency at our threshold are crucial for a detection of a WIMP, of a dark matter a particle. And this is because the rate is an exponential, and you can see there how it changes with these 2 examples. Then one other part of this recipe is the background suppression. For that, as I mentioned, we basically go deep underground to reduce the cosmic rays. We also have this shielding. Even underground, we use this shielding to remove backgrounds from the laboratory, mostly coming from the rock. And we also have we also do a careful choice and preparation of the materials. The third point is the background discrimination. Basically, here are 3 examples of experiments. I'm not going to go deep into the details, but basically, because I am going to explain in our experiment what we do for this background discrimination. But it's basically to find something that separates the electronic recoils from the nuclear recoils. And finally, the large mass, that's what we would like to scale our detectors to ton scale targets. This is the PICO collaboration, with institutions from Canada, the US. We have from also collaborators from Spain, the Czech Republic, India, and Mexico, where the Institute of Physics at UNAM is collaborating. This is a picture of the collaboration meeting in Mexico last year. Our experiment is located at SNOLAB, 2 kilometers underground, in a clean, large space. The environment is close to, it's a class 2000 lab. And this is, SNOLAB is the home of the SNOW experiment, where Arthur McDonald received the Nobel Prize in Physics in 2015. So you have there a sketch of the underground laboratory, where you can see the snow cavern and the several drifts that were basically built after the success of the SNOW experiment, that led into new detectors of not only neutrinos, but also to search for dark matter. We use bubble chambers to look for dark matter interactions. Basically, you can see there a cartoon of our detectors. We have a stainless steel pressure vessel, and inside we have silica, synthetic silica quartz jar. This jar has inside our target material, and then between the jar and the pressure vessel, we fill it with an hydraulic fluid, an oil, basically. All this is connected to an hydraulic system. And what happens is that when we set the pressure and temperature to get this superheated state, when a particle crosses the material, it evaporates a small amount. And that nucleates, produces a bubble. We have 4 cameras ready to take a picture of these bubbles. And also, we have 8 acoustic sensors to detect the sounds when the bubbles are produced. The fluids that we use, we had been using CF3I, and now we have moved to C3F8, basically to explore the spin-dependent coupling of WIMPs to protons. And our detectors operate in this cycle, where we start at about 200 psi. We relax the pressure to 2 atmospheres. This is at constant temperature. And then we wait to happen the nucleation of one of these bubbles. Once that happens, the cameras take the picture. That's one of our main triggers. We also record the sound with the acoustic transducers. And at that time, to avoid any boiling of the fluid, we quickly recompress our detectors with the hydraulic system that we have connected to our pressure vessel. So that basically brings the pressure back to about 200 psi. And then we wait for a few seconds, 30 seconds, and then again we relax the pressure for another of these cycles. So we are constantly cycling in this way and recording the acoustic signals and and taking pictures. We basically have the most boring movie in the world in our detectors. The bubble nucleation mechanism in these superheated fluids, well, it was described by the CITES hot spike model that we actually measured in our chambers, and we have actually changed this model to do calibration of the response of our detectors to the bubble nucleation. Basically, you can control the energy threshold with the temperature and the pressure. By adjusting these two parameters, we can set the threshold of our detectors. And you can see there that it's just basically a competition between the surface energy and the latent heat. The thing is that to produce these bubbles, the dependency is not only on the energy deposited, but also on the stopping power, basically on dEdx. And what you can see there, it's a plot of dEdx versus the energy, where in green you can see the region where we can nucleate, we can produce these bubbles. And inside that area, you can see the recoil of the fluorine, carbon, or iodine isotopes that we have in some of our materials. And you also see the alpha tracks, the polonium-218 and the radon-222. On the other hand, you can see that the electron, the electromagnetic interactions are outside that region. And that's basically because even having the necessary energy to produce the bubble, it is not deposited within this critical radius to nucleate the bubble. And that means basically that we are insensitive to electrons and gammas, and we have measured that. On the plot below, you can see some probability, the probability of nucleation at different thresholds for two materials, for CF3I and C3F8. And this has been, they have been made with in situ measurements in our detectors at SNOLAB, and also in surface chambers that we have, small prototype chambers where we can measure this insensitivity to electrons and gammas. And you can see there that PICO-60 at a threshold of 3.3 keV, roughly 3.3 keV, we have an probability to nucleate from a gamma of 10 to the minus 10. So this is one of the nicest features of our detectors. Now that we have removed the electromagnetic interactions, what we have is the other backgrounds are the alpha decays. The alpha decays are the single nuclear recoils, and basically they are 40 micrometers tracks that produce one bubble. And neutrons are is one of the other backgrounds. These are also single nuclear recoils, but since the mean-free path in our fluids, it's a few centimeters, we can also have multiple interactions. Basically, we can observe 2, 3, or more bubbles produced by neutrons. And to the right, you can see pictures of our detector. On these were produced with an ambi calibration source. Above, you have 5 bubbles produced during these calibrations, and below, you can actually have a multiple event. I dare you to count how many bubbles you can see there in that picture. But well, it's 25 the answer, so you can try to look for all the 25 bubbles. And of course, we expect to be sensitive to WIMPs, and since the mean-free path it's larger than 10 to the 12 centimeters, we expect only one bubble. To discriminate the alpha decays that produce one bubble from nuclear recoils, one bubble produced by a nuclear recoil, the Picasso collaboration discovered that these alphas are 4 times louder than, about 4 times louder than nuclear recoils. And this basically allows to discriminate these alpha events. And you can see a cartoon here where the alpha decay, besides the nuclear recoil of the daughter heavy nucleus, you also have this helium nucleus with a 5 MeV energy. And the track, it's a few 40 micrometers. So this basically has greater power in the production of the bubble. Also, the image that we see, it's indistinguishable between the alpha and the neutron. So we use this discrimination to remove all these alpha backgrounds. And going back to this, the features of our detectors, you can see here this receipt that I mentioned earlier. Our detectors are threshold detectors. We don't measure the energy on an event-by-event basis. We basically set a threshold, and we can measure the nuclear recoils above that energy. The background suppression, we are located at SNOLAB. We have active, passive shielding, water, basically, and we have made a careful selection of the materials. And then for the background discrimination, this is what we do. Basically, we have multiple bubbles produced by neutrons, which are used also to identify neutron sources inside of detectors. And also, we use this acoustic parameter to discriminate single nuclear recoils from alpha tracks. And we have been scaling our detectors very aggressively. We started with Q4 in 2010 and moved to Q60. In parallel, we switch fluids, as I'm going to explain in a few minutes, in a new detector, PICO-2L, and then it moved to a larger chamber, PICO-60. And we're about to deploy our new technology, PICO-40L. And in the future, we are planning to design, to build a PICO-500L, a ton scale detector. There's some cartoons of our first chambers. The one on the top, it's Q4. It's a 2-liter bubble chamber. It's a jar of 15 centimeters radius. And then below you see our largest detector, which is basically, it has only 52 kilograms of our sensitive material. And you see also a multiple bubble event produced with our calibration sources. This is the family of our detectors. As I mentioned, we started with Q4, this 2-liter that you see CF3I. We also scale it to Q60, a 40-liter CF3I chamber that ran from 2013 to 2014. And then we switched fluids to C3F8, and we started with a 2-liter chamber called PICO-2L, and then PICO-60, our C3F8 bubble chamber, the result that I will present you in a few minutes. And then we are deploying in early 2018 PICO-40L, and we are planning our larger chamber, a ton scale experiment, PICO-500L. This is a picture of our first detector, Q4. As you see, it's a modest hardware experiment. You can see our data acquisition system, our computers, and also in between those white tanks and the computers is our hydraulic system. It was just a piston to compress and expand our chamber. Inside those water tanks, we had our pressure vessel with the filled with hydraulic flow fluid, and inside the quartz jar with the CF3I. How do we do the data analysis? Well, basically, once we take these pictures, we have an algorithm that searches for clusters among pixels, and we are comparing consecutive frames, and that's how we identify the bubbles. At the same time, we have pressure sensor, basically to measure the change in pressure when the bubbles are nucleated. And you can see on the picture the blue trace with the green fit. That's our acoustic. That's our pressure sensor. And the acoustic sensors, the piezo's. In this chamber, we had 3 active ones, and those are the pink colors, where you can see the traces of the piezo's once the bubble is produced. And by doing an examination of this acoustic signal, we can also determine if it is a neutron or an alpha track. And this is basically what we use. We have 3 ways of counting. We have the images, where we can count how many bubbles we have. Also the pressure. The pressure also gives us the number of bubbles, and the acoustic parameter. And you can see there the power, basically the frequency spectrum of one of these signals. In red, it's an alpha. The neutron is in blue, and our timeouts, when there is no event, it's in green. And you can see that there are some frequency bands where we can discriminate the alpha from the neutron. And then to the right, you can see a plot of the acoustic parameter versus the bubble number. So you can see 1, 2, 3, 4 bubbles, of course, produced by 2, 3, and 3 and above by neutrons. And then at 1, you can see the bubbles produced by neutrons and alphas. The neutrons are in the blue area. Those events were obtained with an ambi source. And in red, you can see the alpha backgrounds in our detector. Most of them coming from the radon 222 chain. And you can see how this acoustic parameter, it's normalized to the single bubble recoil-like events. But you can see how it separates these two regions for single bubble. This is the detector that we ran first in 2013 and 2014 with CF3I, and now last December with C3F8. It's our jar made of this synthetic silica. And around here during round 1, you can see in gold the acoustic sensors to record this acoustic signal that I just talked. And then this detector is enclosed. It's in the picture to the right. You can see that when it is placed inside of the pressure vessel. Here we have it inside of the water tank that we use as to shield from mostly from neutrons in the produced in the rock in the cavern. You can see some pictures of the day that we deployed the detector, and also you can see a close picture of our pressure vessel with the viewports. You can see the red color there, which is coming from the LEDs that we use for illumination. And in this run, we had only 2 ports with cameras, and the other 2 were blanked for this first run. We ran our detector, as I said, in 2013 and 2014. We collected more than 3,000 kilogram days of the dark matter search data between 10 and 20 keV. We didn't observe multiple bubbles. So basically, we put a limit on neutrons, on the number of neutrons that we had on our detector. But we observed a population of events that sound like nuclear recoils, but were clearly not WIMPs. This was some anomalous background, and we know that they were not WIMPs. Well, for several reasons. They were unevenly clustered in space, and what we found is that these events that you can see in the bottom plot to the right, they had a distribution over the expansion time. That means that we were observing this on no background at early times after the expansion, and this is of course something that dark matter shouldn't do. You can see there a comparison of the alpha backgrounds that are homogeneous distributed over the expansion time, but we have these decays, these events decaying away quickly after the expansion. Above, you can see this acoustic parameter, this normalized acoustic parameter with the alpha population in red, and this filled with red color, and the unknown background, which is just next to the nuclear recoil band obtained with the ambi source. So for these reasons, that's why there is no possibility that this could be produced by dark matter. To investigate this, and in thinking of the possibility about the fluid that we were using, this was with CF3I. We changed our small detector Q4 that you see on top for a new pressure vessel and a new detector called PICO-2L with a different fluid. And it was C3F8, basically to go for spin-dependent sensitivity and to operate at low energy thresholds. And well, after running this small detector, we found also this anomalous background. One interesting result that we obtained with this detector is that we observed 2 peaks for the alpha tracks from the chain in the radon 222. We were seeing 2 different alpha energies, and this is basically what we think is the first observation of alpha calorimetry. And moving now to the reason of this background, these anomalous backgrounds. Well, we did some filtration of the water that we have as buffer in our detectors, and this examination revealed some material, some particulate content, mostly quartz and stainless steel. And basically, we are blaming that the reason for this anomalous background is that we have a combination of these particulates and water droplets that basically lower the bubble nucleation threshold and produce nucleation in our detectors. Basically, these water droplets attach to the solid particulate, and then we have this lowering of the threshold, and then that this is producing these anomalous backgrounds. And to test this hypothesis, well, we did several modifications, additions to our detectors. In PICO-60, besides the new fluid, we installed an online filtration system to study the development of this particulate contamination. And in our smaller chamber in PICO-2L, we replaced some components, and we optimized the operations of our chamber. And I'm going to show you what we found with the smaller detector with PICO-2L. To the left, you can see the results before these modifications or additions after 32.2 live days. And what you can see there is that we have this candidate, this in red, the mysterious, the anomalous background. And after improving our cycling, our cleaning procedures, and unfilling procedures in the detectors, you can see in more than twice the exposure, in 66.3 live days, that we observe only one event. And this is actually consistent with our neutron expectation coming from simulations. So basically, we were able to remove these backgrounds in our smaller detector. We did the same in PICO-60, and this is basically a summary of what I just told you. We started in 2010, 2011, where we discovered this background in our 2-liter chamber using CF3I. We scale it because we wanted to increase the statistics, and we observe also this anomalous background in PICO-60. In parallel, our small detector, we moved to another fluid, C3F8, and we also observed this event. We came to use this filtration of the water that we use as buffer, and we found these particulates. We tried to remove the particulates, and with our 2-liter PICO-2L detector in 2016, we succeeded, and now we try to basically scale in 2017 to PICO-60 to a larger chamber, now that we have controlled our backgrounds. This is the physics run that we had. We started on November 2016 up to January 2017. We completed 30 days lifetime. You can see to the right the filtration and basically the better filling procedures that we had. We cleaned all the internal components to a military standard 1246C level 50, and basically all the inner components were cleaned at this specification. We operated at 3.3 kV energy threshold, and we collected more than 1 ton a day of dark matter search data. We did a blind analysis. Well, actually, we call it a deaf analysis because we didn't check the acoustic parameter during the data taking. And what we did keep observing the number of bubbles in the detector. And we observed 3 multiple events consistent with our background expectation. And you can see also a picture there of the cleaning that we were doing on our detector. We had a fiducial mass of 45.7 kilograms with a selection efficiency of 85%. And after all these cuts that we have, they are described in our latest publication, the acoustic parameter, also the pressure sensor that allows to discriminate events near the wall of the detector, and also the cameras. We define our fiducial volume, and we observe, of course, this fiducial volume was obtained with AMBI calibrations. We used AMBI calibrations to obtain this volume, and also a pre-data set before the 30-day exposure. We observe after that 106 events after the 30 days. What you can see on the right is the acoustic parameter. In red is the WIMP search, and in black is the neutron. The neutron calibration obtained with the AMBI. And we also use neural network score in our analysis. And after unmasking, we observe no nuclear recoil candidates in the 30 days. This basically, this observation of no nuclear recoils and 3 multiples matches our neutron background expectation obtained from simulations. So this basically allows to place these limits on the spin-dependent WIMP-proton couplings. We have improved our limits by a factor of 17. You can see them in blue to the left, the PICO-60 C3F8. In red, you can see they are the same chamber, but when we fill it with CF3I, and you also see the results there in magenta, the PICO-2L results that we obtained in 2015 with our 2-liter chamber. To the right, you also have you can also see the spin independent WIMP nucleon cross section, and of course we are only here. You can only see from 1 to 100 GeV. This is near the low WIMP mass region. And we have, you can also see there the results from all our chambers compared to results from Panda X LOX and some other detectors, some other dark matter detectors. Of course, our greatest sensitivity is for the spin-dependent WIMP-proton coupling due to the fluorine that we are using. We also place some limits on compare our results to the LHC results, and instead of trying to plot their limits that highly depend on the effective model, what we did is basically place our results in their plots of the WIMP mass versus the mediator mass. So that's what you can see there as an example only for the mediator exchange in the S channel with only for the 4 free parameters, the dark matter mass and the mediator mass. That's what you can see in that plot. And assuming universal mediator coupling to quarks of 0.25 and the mediator coupling to dark matter of 1, you can see that we have obtained an interesting region in WIMP mass for mediator masses between 1 and 100 GeVs. And also, we can compare, for example, the spin-dependent coupling to proton and neutron obtained by LOX and Panda X, and we can restrict some space parameter. This is an example for 50 GeV WIMPs, and you can see there how we can using results from coupling to spin-dependent coupling to neutron, combined with our spin-dependent coupling to proton, restrict the space parameter in this area. So you can see more details on these effective coupling parameters, AP and AN, in that reference. So what are we moving on now? Well, we are now building PICO-40L, and it will be deployed this 2017 and start taking data early 2018. Here, to continue removing these backgrounds that we believe are coming from components above our detector, we have basically flipped our chambers. We call it the right side up chamber. And it will be a similar size as PICO-60. In parallel, the group at Northwestern University have recently succeeded in operating a xenon bubble chamber that has the acoustic signal, basically the acoustic power to discriminate alpha decays, and also has the scintillation present in xenon. And we are also aiming for our large detector PICO-500 ton scale chamber that we plan to have ready by 2018, 2019. And this is interesting because what you can see there in that plot to the right is the spin-dependent region for a comparison between the xenon detectors, such as LZ, and our detector PICO-500. But the interesting is that the neutrino floor in xenon is way above. It's about 2 orders of magnitude above than for C3F8. So basically, we could continue exploring lower cross sections, 2 orders of magnitude below, when xenon detectors start seeing the neutrino floor. So this is something really interesting that goes into our technology. Finally, well, this is a picture of our detector of our PICO-60 chamber deployed last summer, 1 year ago at SNOLAB. You can see there the chamber being placed inside of the pressure vessel, inside of our water tank. And this is a very nice picture of our detector. I'm going to jump now to my conclusions. Our chambers are producing world-leading direct detection limits. We are using fluorine targets to explore this spin-dependent WIMP-proton limit. We have improved our results by a factor of 17. And in parallel, we have controlled our anomalous backgrounds. They have been understood. And we are ready to continue now testing using a different, slightly different chamber, PICO-40L, coming early in 2018. And we believe that our technology is the bubble chamber technology is ready to be scaled up and to ton scale. And that's why we are going to build PICO-500L. So this is an exciting field. And I think it's also an exciting future, promising future for our detectors. So it's a bright future for an amazing science if you want to be optimistic, or if you want to be pessimistic, even a dark future for amazing science. Thank you very much, and I can answer some of your questions. You have any comment?
Okay, thank you very much for this very clear overview of the PICO experiments. And unfortunately, the so far is no results, but I think we can be confident that you will achieve a much higher sensitivity in the future. Now, before we pass the questions from the floor, let me remind you that you can ask questions via the Q&A your YouTube, or via Twitter. So now I will pass you to Eric, and we will have the questions from the floor.
So I have a question for Eric. Eric, first of all, very nice your talk. It's very impressive what is doing PICO. And yeah, I have a question that was the doubt in the beginning when you, I mean, it's a little bit how it works, the detector. So each time that there is a bubble, then you have to you have to wait that the bubble disappear and kind of reset the detector. After each time that appear a bubble and disappear. So more or less, how much time is needed to wait for the liquid to become again in the ideal state, wait for next bubble and so on and so forth?
Yes. So I miss it. Here you can see a typical in this plot at the bottom right. You can actually see the elapsed time between a typical event. So we basically start at 200 psi, and we leave it for about 30 seconds, and this is to recondense all the fluids. And then after that, we relax the pressure to the 30 psi, the 2 atmosphere, and that's where we start where we open our window to wait for a nucleation. And as you see, that takes between about 3 minutes, 3 seconds. Sorry, it's seconds, 3.5 seconds, and then we wait for a nucleation. So one thing is that if we get the bubble, then the cameras trigger, we record the acoustic information, and then that's when quickly, in a few milliseconds, we compress to 200 psi. So we have a dead time there of about 30 seconds waiting at 200 psi to recondense the fluids. If nothing, one thing that I have to mention is that if nothing happens in, we have been changing this time, but if nothing happens in 500 or even 1000, or if the chamber is really stable up to 2000 seconds, we again recompress our chamber, even if there was no event. And every 10 events, we, instead of the 30 seconds, we leave it compressed by 300 seconds. So this is basically the operation cycle of the detector to have our fluids in a position to efficiently record the bubble and to have all the fluids recondense.
So that means that because I don't know, in case other type of detector, PICO is faster or slower in the sense of each time of I don't know, with xenon experiments, they also have to wait for reset all the
yeah, I think that's yeah, I'm not aware actually of the times that they have for these dual phase chambers, but as you can see in our efficiency cuts and our exposure, so we have high exposure times as well. I mean, it's not a large amount of time that we are losing in this cycling. Actually, you can see here, I think I have it somewhere in one of the slides, the exposure. We have an 85% WIMP selection efficiency, right? So it's not a large amount of a large loss, right? Of time and in all the cuts that we use. I guess that's a different question related to what you were asking only about the time, but even combining that, we have a large efficiency. And we did also some calibration during the run from November, the end of November 2016 to mid-January. We had 30 days of lifetime. So yeah, we have some lost time, but it's a reasonable.
Yeah. Also, it's better to wait a bit to ensure that the data is well taken. No? I mean,
Yes.
Yeah. So another question. I mean, I don't know if other people have more question, but yeah, also related with the detector and all the upgrade that you have done in the coloration. When they scale the geometry of the chamber, does it play an important role in the sense, because in the case of Cube, the chamber was a little bit more round, but then when you show the last chamber, they were very elongated vertically.
Yes. Yes.
So there is a reason to make it more long, or just
yes,
more or less, yeah.
Yeah, the reason is because most of the components that here in this cartoon, for example, we try to keep the active fluid that it is in blue on the image to the right. We try to keep it separated from the region above that you see on top, the bellows, the cooling coils. So those places we try to, since they have some components that could produce backgrounds, we try to separate our detectors from that area. That's why you see that above the blue volume, where we have in this case the CF38 target, we have this water buffer to keep separated our target fluid. So that's basically the main reason, and to have a longer chamber. In our smaller detector, we had only 2 liters of fluid. So they were still separated by this water buffer, but that was the geometric restriction to design the detector this way.
Mm-hmm. Ah, okay, good. So yeah, I don't know if there are more questions for other people or no.
I have one. Can you hear me?
Yeah.
Yeah. Okay. So you at some point showed that with this, when you were comparing the xenon and your fluorine targets, that the neutrino floor would change. But the question there is, if you take a specific dark matter candidate, how do those cross sections, how do those recoil cross sections change?
So
yeah.
You mean on this plot?
Yeah, on the one on the lower right.
Okay.
So yeah.
But yeah. I mean the dashed lines on black and blue are for neutrino scattering. So it's not for a dark matter. It's basically the coherent neutrino scattering on nucleus. So that's what it would be for xenon, and that's what it would be for C3F8.
Yes, of course. So my question is, okay, what if you would put a dark matter, like choose, say, 100 GeV dark matter particle with a specific coupling, right? So how does the cross section change if you're using xenon or you're using your fluorine?
Yes, but that will change the solid lines, right? That's the one that basically we would move to according to the dark matter candidate coupling that you decide.
Exactly.
Black and blue will not change. These, of course, are the standard that we use, that we report in our publication that you can see in green. But of course, I mean, I guess the answer is yes. That will change the solid prediction of one of the other or the other detectors. But I think that the main message here is that even if that changes, we could, with our detectors, explore these two orders of magnitude compared to the xenon.
Yeah, because so the point is that if you fix a mass and a coupling, say you calculate the cross section with xenon, right, and you get something like, I don't know, 10 to the minus 44 centimeters squared, right?
Yeah.
So that you say, okay, that is under the neutrino floor for xenon.
Yes. Mm-hmm.
So you say, okay, no, you cannot watch it. And you say, oh, maybe you can watch it with your fluorine thing. But then you have to do the same thing that you did for neutrinos, and you have to calculate the cross-section with the same coupling, with the same mass, with the fluorine. And if in that case, so the question is, does that change? Yes. Or does that can go down to 10 to the minus 49 or something like this?
For fluorine, it will certainly change as well, right? When you pick the other mediator.
Right. So the question is, by how much would you say it changed? Because if, okay, you can say, all right, the neutrino floor is lower, but then if the cross sections are also going to be lower, it doesn't make a difference.
Yeah. Well, well, I mean, I'm not sure how much it will change, but not by that much. That's what I think, right? Because it will be the same similar coupling that will only change by the nucleus, right?
Mm-hmm. Okay. All right.
I don't have at hand the amount of how it will change, right?
Okay. Yeah, because that's the question regarding, how the neutrino floor changes. If the neutrinos can change their cross section, then okay, what happens with the dark matter?
Yes, but at the end, I mean, at the end, what we do is to have a standard framework to be able to compare the cross sections, right? Assume the same set of similar couplings in this case for these plots, right? For the distribution of dark matter and other to have this standard effective couplings AP and AN, right?
Mm-hmm. Okay, thank you.
Yes, thank you. Hello, I have a related question to that plot, actually. Those PICO-500 results, when can we expect that line, actually?
Yeah, this is the expectation with the chamber that we are proposing. We are requesting funds to build it, and we could have it built and taking data in less than 2 years. And so I guess this is we are talking about a time framework of 2 to 3 years, if being very optimistic, right, to reach this level.
Okay, I don't know if there are other questions.
Yeah, I have one more.
Yes.
Yeah, Eric, there is a study with the cross section, WIMP-proton cross section, that is in which PICO beats all the other experiments. But my question is, I mean, that is very impressive, but why PICO is completely insensitive to the WIMP neutron cross section? It's because of the.
It's because of the pairing. It's because of the pairing of the nucleus, right? So basically, we have an extra in this proton, and that's what gives us sensitivity to WIMP-proton. We also have to neutron, but of course, in a not as good as the xenon nucleus. So it's basically with the number of protons and neutrons, right, that we have an extra one in this in the fluorine. So that's why we have these limits on better limits in WIMP-proton. Yeah. So it goes with you have a pair or an unknown pair, right, in the number of protons and nucleus, and that's basically the difference between fluorine and xenon. And in fluorine we have the preference to this proton, and in xenon to the neutron, and that's why we have this effective coupling AP and AN for both isotopes.
Yeah. So in that sense, it's not possible to add something to the target inside PICO to make it also sensitive to neutrons, or it's just by construction was made for proton directly? Proton.
Yes, I understand your question. Yeah, I mean, we are sensitive. We pick fluorine to be sensitive on this WIMP-proton coupling. Of course, that we would need to select a fluid, an isotope that would have, in this case, would be like xenon for the spin dependent WIMP coupling to neutron. But that would mean to use a different fluid. Something that, as I showed, the group at Northwestern, they have been working with a xenon bubble chamber, right? So they are working with a prototype, and it is operating that would have the scintillation power of the xenon detectors, and also the acoustic discrimination that would be, of course, sensitive to this other coupling. One of the nice features about our detectors is that it can be built with any. I mean, we can make a bubble chamber from basically any fluid, and we are exploring also other fluids beside xenon to reach different space parameters. So it's all this. This technology has this feature to be able to move to other fluids and explore other couplings, not only the spin-dependent WIMP-proton.
So yeah, and also related with this, because there are a lot of effort people doing to try to measure to try to predict or to constrain also the coupling between WIMPs and electrons, because in some sense there are some limit using xenon or for very light WIMPs for under 10 GeV, also MeV. Is it possible to do something similar with PICO, or PICO is completely would be hard for the case?
Yeah, we would have to. Well, our detectors are insensitive to electron recoils and basically electromagnetic interactions. We, on purpose, of course, we operate the chambers and we have at thresholds where we are insensitive to remove all these electromagnetic backgrounds coming from components, some from radioactive decays. So our technology, as it is now, of course, it's insensitive to these electron recoils. If we would like to explore, for example, coupling, in this case, electron recoils, of course, that means that we have to lower the threshold, as you saw in this plot. But of course, that means that we have to be more careful with the materials that we use near our target volume. So that would be probably possible in a larger detector where it self-shields, and still you see here that even at 1 kV, the threshold that you actually, I can point here, right? The threshold that you can see here, it's the probability of nucleation is 10 to the -3, 10 to the -4. So it's still a very, very low probability to produce an electronic recoil. So the answer is no. We cannot use that as we are now to search for that coupling.
Yeah, I mean, yeah, it's true. I mean, it's a trade-off of if to deal with the electron background or not to deal with the electron background.
I mean, the nice feature of these bubble chambers is that we are insensitive to these electron recoils, right?
Exactly. It's a problem to not deal in this case.
Yes. Yes, I guess that it would be a problem to explore this coupling.
Yeah. Okay. Thanks for the. I mean, yeah, I don't have more questions for the moment. So
yes. Hello. So if there are no more questions from the floor, there's a question and a comment from in YouTube. There's a question from Xenon Wanton, and there are two questions actually. So first question beforehand. Can we see some pictures of the events? Those bubble chamber tracks are awesome.
Yeah, they are very nice, and I showed several pictures along the talk. Here, for example, you can see this 25 bubble event that we observed at the bottom. So you can count here how many bubbles here. This is basically they were made with an ambi calibration source.
Right, and the second is how to construct the FV.
Yes, the fiducial volume that it's basically obtained. I guess here is here is the region of the fiducial volume, and of course this is obtained with our ambi calibration source, and also with a pre-physics data, and it is a set of cuts using the images and also using the pressure sensor that defines this fiducial volume. And this is in order to remove wall events here near our in this area, right? This is the jar, basically the edges of the jar, and it is to remove these wall events.
Okay, thanks. And then there's a comment from Senheinemeyer regarding page 45. And he says the limits were shown versus SUSY predictions, and those are relatively old. So the point is that updated limits, lie somewhat below and are touched only a little bit by the current PICO results.
Yes, that is correct. We actually last week, one of our collaborators that was in a conference in Europe was approached by, don't remember his name, but it was the same comment that, yes, we have these old limits and we are working to set this plot with the latest ones. But on the other hand, when you see the limits that are mentioned here by Sven, the favorable region on these new limits are just around the corner for our detectors. I mean that with our PICO-40L, we could reach that favorable area for these updated results. So I guess that the comment is, yes, we are using this old, relatively old, but the new ones are pointing, are just right next to the corner to our next detector. So we will work, of course, to get these new predictions, SUSY predictions, for our next publication.
Okay, thank you very much. I think there are no more questions. Right, so let's thanks again the speaker, and we'll meet again for our next webinar. So